So I want to answer these two questions. Why do we use d in dy dx? Why don't we use a different letter? Or what's the significance of using the letter d? And this other question, why does the integral sign look like a big S? So first thing, why do we use a d? You might think d is short for derivative. That would be wrong. The reason we use d is to represent change. Dy dx, you could read that as the change in y for the change in x. And where did we hear that before? We heard that in algebra. And your algebra teacher may have used the shorthand notation when he talked about slope and used this little triangle and said slope is delta y over delta x. What is this delta? This delta is the Greek equivalent of the letter D. So it's no big surprise that change in y over change in x becomes dy dx when we find the derivative of a function with respect to x. We are really finding the formula for the slope of the tangent line. Okay, so why do we use the integral sign? Why does the integral sign look like a great big S? This one is equally cool because if you remember from your calculus class the way your teacher may have got you interested in the idea of an integral is the teacher may have drawn a function f of x from a to b, and he told you that the way to find the area under that curve is with the integral. You take the integral from a to b of f of x dx. So let me write area. And from this we know the steps and it consists of finding the antiderivative of f of x. We evaluate it at b, and then we subtract evaluation at a. And that will give us the exact area under this curve, f of x from a to b. Stepping back, we might remember a picture like this. To approximate the area under a curve, we could use these rectangles. And this is using Riemann sums to find the area underneath a curve. What is this doing? This is, if you go from the top picture to the bottom picture, you see delta x, the width of a generic rectangle, is shrinking. What's the formula for the area of a generic rectangle? By generic I mean a general rectangle. So for that, we can remember, if we just took this generic rectangle right here, the height is f of x. So let me write that. This is f of x. And the width is delta x. So if we added up each one of these rectangles, whose area is each f of x times delta x, and we did that with smaller and smaller values for delta x, we would approximate better and better the area underneath this curve. And here's the notation for that. You may remember this. I like to build this formula from the inside out. Here is the area of a generic rectangle. Oops. F of x times delta x. Here we are summing from a to b all of those rectangles. And the last step is to take the limit as delta x gets small, or delta x goes to 0, of this entire expression. And you can imagine that the area would be the solution to this problem right here. So I still haven't said why this integral sign looks like an S. Turns out that Leibniz is the one to introduce this symbol, and he meant it to be shorthand notation for summa. And this summation sign here is a sigma. These are both meant to be S's. This is the Greek S, and this is probably the Latin S. And Leibniz used it to denote a summa. So that is why this integral sign looks like an S. You could even read this in a slightly different way. This is the area is equal to the sum of the rectangles, the area of the rectangles from A to B. You can see how similar these two expressions are. And this also goes back to why we use D for delta. That's it. I hope that was helpful.